what we had a discussion on in the last three sessions of our on materials involved in bridge design and bridge construction. What happened? Nobody wants to take an initiative. So we should start with a mini quiz every day morning, every day, every session, to say what did we do in the last two classes or last three classes, for everybody to see whether they were attentive or not. Yes, anybody? Otherwise, I need to call out people. Yes, come on. Okay, anything else? And now if I have to ask, not from you, from the others, we discussed on concrete, but what kind of concrete did we discuss?
Confined concrete.
Huh?
Unconfined concrete.
I couldn't hear it clearly. Can you repeat again? Can you repeat, please? I couldn't hear it clearly.
Hello, hello, sir. Unconfined concrete.
Confined concrete.
And unconfined concrete.
Unconfined concrete. That's all. Okay. All right. So we looked at, and nobody thought we didn't do anything about the steel, right? Or we did something about it. Okay. So we got an introductory idea about the different materials that go into bridge construction. We started off with steel. Steel being covering, just as a basic background rather than in depth about it. From the material point of view, base steel for reinforcement, steel for structural performance. Then we looked at unconfined concrete. Then we looked at elastomeric rubber as a load transferring media to be used in bearing and in accommodation of various kinds of deformations. Then we looked at PTFE, polytetrafluoroethylene, as a means to reduce the frictional resistance in between the moving components of bridges. These are the things that we looked at. Now we will move on to the another important, and of course we covered stainless steel because it's one of the materials that we use it for the purposes of corrosion resistance property that it has. So we will now move on to the other aspect, another material which we use, and probably the one which we use the maximum. And what is that? What's the material that we use maximum in bridge design and construction, other than whatever I mentioned? No idea? Have we covered everything? Steel, structural steel, reinforcement steel, stainless steel, then unconfined concrete, then elastomeric rubber, potent PTFE. Is there any other material which I think which we use the maximum?
And on pre-stressing steel.
Pre-stressing steel we covered in a small high tensile steel we covered in the part of the steel itself. So, okay, it was a semi-trick question, you can say. The one material which we have not talked about, which we will talk about today, is the confined concrete. Now, you'll start wondering what is confined concrete. Okay, so we will start by, I'll start by sharing my screen now. Please confirm when you are able to see the screen. Are you able to see my screen?
Yes, sir.
Okay. So we will deal with confined concrete now. So to understand this confined concrete, let's go back, do a little bit of recapping on the concrete itself. Okay, and the effect of confinement. Okay, so at a essentially the confinement of concrete leads to two aspects. One is the fact that its strength increases, but its strength increase is not that exciting. It's a small increase in the strength. When we do strength, we measure it with what? We measure it with the value called FCP, that is the peak strength to which the concrete goes to, which if you want to look at for different grades, this will be the peak strength. And we also see how it affects once the grade of concrete increases. We have seen what's the pattern in which the peak strength goes. It has, but it increases. The confinement has a much smaller impact. It's bigger, and the most interesting effect is increasing the deformation capacity. Okay, so basically we understand concrete as a material with little or no ductility, though there is a classical definition of ductility which we recall. Can somebody recall what is the definition of ductility? Absolutely. Don't ever forget that in your life. The measure of ductility is the ultimate strain by yield strain. Okay, and yield strain is the point at which the so-called linear stress strain behavior is lost and it goes into the non-linear zone. So in the case of concrete, we theoretically look at some points, all these points, the strain here as the strain at yield, and we look at this as the strain at failure. Now, some general knowledge question. What do you think the lab tests show as the failure strain of concrete at the real failure time? What do you think is this epsilon Cu observed in the lab? Just 1 second, please. 1 second, please. Just hold on. I need to. Bridge management system for the country, and I'm one of their advisors to look at the structuring and the documentation for it. So that I need to give my feedback on one of the reports that they've given. So I had to take the call from the Director General. Okay, fine. So let's continue with that. So what we were seeing is that concrete as a material is practically not ductile in that sense compared to steel, basically from that point of view. But nevertheless, it has some amount of internal ductility from the classical definition of the ratio of epsilon Cu by this. Now, question I asked you was this 0.0035 that we talk about. In reality, is this the value? Can concrete not take strain more than this? Of course, what is the graph you're seeing is that of an unconfined concrete. I'm still talking about unconfined. We'll connect up with the confinement a little later. In reality, what happens is these test results show the what we call it, the epsilon Cu for unconfined concrete ranges from around 0.0035, 0.004 till about 0.006. In that range is where actual work, and for all our design philosophies, we use, or what we call as, you all understand the term constitutive relationship. The relationship that's the between the stress and strain for concrete, which is in terms of a parabola for up to certain height and a parallel line to the x-axis thereafter until point. That constitutive relationship, to define that, we use it up to 0.0035 because this is the highest maximum reliable value that we generally have seen from the lab. Otherwise, it can go little higher. Now, we also know that the concrete is very good in compression. Good is in quote marks, in the sense, though it is good in compression, it doesn't satisfy all the characteristic of a good compression, which means it doesn't show enough ductility, etc. Because any strength which collapses suddenly is not good for us from safety point of view and from human safety point of view. So concrete has got these characteristics. It is virtually not ductile and it is good in compression. Whereas when you look at steel, steel has got a extremely ductile material. That means your epsilon U or epsilon T, epsilon U versus epsilon Y. This ratio is enormous for concrete, for reinforcement. But it has also got a very high strength. So when we talk about confined concrete, primarily we are talking about an interface between use of reinforcement and use of concrete judiciously. So the question is, while concrete is good in compression, steel is very good in tension, concrete is very brittle, steel is very ductile. So obviously, wherever we use the steel, we must use it steel in all those locations where tensile strength is required. And concrete you must use where we need compressive strength. And if you reverse it, we had it. We are in deep trouble. Okay. So when we use confined concrete, it's basically a combination of reinforcement steel and concrete. Then you can come back to the more commonly understood definition of reinforced concrete. But we are still not talking about reinforced concrete. We'll talk about confined concrete and what is the effect of confinement on concrete itself. That is what we would like to understand in the next few slides. Okay. Now let's think about, imagine a situation where we have a column subjected to a lateral load and it has no ties. Then what will happen? With a single diagonal crack, the column will fail. This is a very poor behavior for it, right? Next comes the question, instead of doing that, we introduce horizontal ties at interval. It will take some amount of the lateral load by formation of this yellow colored patch is what is called as the compression line of strut, and this red color is the tension tie which will take, and with that process this horizontal load without failure will take it to the base. So it's an improvement on this poor behavior by introducing this tie. But if you notice one thing here, you will notice that the compression strut is occupying very small portion of it, and a large portion of it is still having no compression. Now we do this, move it further, and we make these ties even closer. If we make these ties even closer, we will find that almost all the space within the longitudinal bars and the horizontal ties, we will bring it in the state of compression. Okay, which means what? We have essentially improved the utilization of concrete to the most efficiency. So if you want to use the improve the efficiency in the usage of concrete, introduce closer spacing of ties. So this is one positive influence of the presence of the transverse bars. There's another presence and positive influence which you can see in the left picture. Under the action of axial load, what happens is this concrete, the reinforcement bars tend to bulge out and buckle, and the presence of closely spaced ties prevent that. So the positive influence of transverse bars take place. One, it improves the utilization of the concrete itself by keeping most of the concrete in compression even under the action of lateral loads. And the other one is it introduces a restraint against lateral buckling for the main longitudinal bars. So two effects that you see, but we will stay strictly still focused on the effect of reinforcement or the confinement on concrete, though it has a secondary benefit in terms of preventing the buckling of the longitudinal steel. Now to understand this performance of the tie, you can look at the two different detailing, As you can see here, when the axial load is compression, you have a detailing here where the closed tie has a 135-degree loop. The question is, how do we make the confining concrete effective? Confinement effective. So in order to achieve an effective confinement, you must have this 135 degrees bend at the end so that the open ends of the tie are anchored into the core of the concrete. If on the other hand, you tend to do a 90 degrees one under certain loading conditions, these ties will open out. It will not provide the confinement. So it is sheerly a waste of steel to provide for a 90-degree bend and leave it at that. So from now on, you must make sure that your detailing is such that you have no 90-degree bend of the confining tie. The confining tie must always end in this 135-degree bend. As you can see, the angle for this bend, for that line, from there to this angle, the 135 degree. With this, you will ensure that all the bars which are not even tied also get provided with some amount of restraint from transverse deflection of the longitudinal bars. So there is no opening of the ties with the, so this is one important lesson that you must take back with you, stating that you will not detail out any tie which does not have a 135 degrees bend at the end. Okay, no 90 degrees should ever be accepted by you in any drawings that you produce. Now, what is the, take a look at this section. Let us take a squarish section wherein we have only one tie. Even in this one tie, what happens is the confining activity is restricted to the location at which the tie goes around this vertical bar. And this areas, the confinement is less. To improve this, what happens? You introduce another tie in this location, then the area provided with confinement increases. So in terms of detailing, this is better than this, right? Now comes the question, for a circular column, if we have a series of cross ties like this, as opposed to providing this, what would be the confining thing? That is a thing that you should think about, and let me know sometime. You can discuss among yourself and then send me what would be the confinement area if I had only the outer circular bar which provided the, which acts as a tie, versus this obviously similar to this. You will have a tie zone like this, but very tedious to provide. But as opposed to this, if I do this, what will be the confinement, effective confinement to the concrete? That you should think about it and let me know in the next class. Okay, so the question is, if you want to achieve good confinement, you must tie as many bars as possible. Now, as you can see, if we have ties which are sparsely, that you saw in the cross section. Now, if you take a look along the height, the moment you have closely spaced ties, you have very small areas which do not have the confinement effect of these ties. If you have far spacing, you will have much smaller, much larger areas of concrete which are not seeing the confinement effect. So now comes the question, what should you take away from this? You must always detail out what should be the closest possible provision of ties that you can give. Closest possible spacing of ties is the best, but of course you have to keep it within the limits of practicality. And I would like to see if you can work out what should be the, for generally for bridge sections from first principles, can you work out what should be the maximum length of the unsupported length of the, or the minimum spacing that is good for confinement? Can you attempt on your own to work out how will, from first principles, work out what should be the minimum spacing that will provide for the maximum confinement to the core concrete? So in bridges, generally the situation in the second and third is not acceptable. We should always conform our detailing to what is the leftmost detailing, that means closely spaced tie. And as I told you, you work out what should be the spacing that will ensure this kind of a behavior for you. Okay. Now, the effect of confinement has got another aspect to it. As we saw last time, when you apply concrete with compression, one, it undergoes an axial deformation, and second, it undergoes a transverse bulging or transverse extension. The effect we saw it, we call it Poisson's effect. But once you have confining steel, you will notice two things that happen to concrete. The amount of axial strain also reduces, and the amount of transverse bulging also reduces. Both of them reduce. Okay. And that happens because now there is a transverse steel that is present in concrete. It goes into tension, and that in turn, this red line represents the tension into the bar. And for equilibrium purposes, it will induce a corresponding compression or the confining pressure on the concrete, which you can understand from this cross section, that the confining bar is in tension and the bar is in tension with an equilibrium of pressure like that. This is equivalent to the confinement stress and pressure, or you can look at it and visualize as if there is a radial confinement provided. This is an example of a circular section with a tie and the longitudinal bar. So the tie provides for the confinement force, and if you look at it, you call that as an F confinement stress, if you want to call it. That is an effect induced by merely presence of closed loops. Closed loops are the most effective form of confinement that you can provide for. Okay, so the question is, if you recall the stress strain curve for it, you have this as the stress strain curve for the unconfined concrete. Now, can you tell me what will happen when I provide for a closed loop confinement to this section? As you can see here, if you have this radial confinement, what will happen to the stress strain curve? Yes, please. I hope not all of you are not sleeping. What? Don't use the word. Okay. Yeah. Okay. Okay. Okay, good. So you have got the three critical changes that will happen due to confinement well understood. So basically your epsilon Cp Cu will become epsilon confined Cu, epsilon Cp will become epsilon confined Cp, and epsilon Cp will be FCP will become F confined Cp. All of them go up higher under the action of this. That means FCP increases to FCP, FCU, epsilon Cu increases to epsilon CCU, and epsilon Cp also increases to epsilon CCP under the action of confined thing. Now, what does this mean to us? If you notice, of course, this drawing has been made in such a fashion, it looks as if the change from FCP to FCCP is significant. In practice, change from FCP to FCCP is very small, much smaller. But what's more interesting, or the most interesting, is the amount of change that happens in epsilon Cu. From epsilon Cu going to epsilon CCU is the most interesting thing that happens, because this whole behavior has been codified in the form of a model proposed by Mander. And in this Mander proposal as to how to develop this, it basically says you basically have this epsilon Cu, Cc, this, it's based on the confinement pressure. You have all these relationships that are derived for FCC, that is the stress in concrete at any time due to confinement pressure. This and then this, all this eventually reduced to a simplified form wherein the confined FCCO is linked to one single parameter called effective confinement. This FL, this is the confinement effectiveness. Okay, and that effective confinement depends on three parameters. Which is Ke, rho s, and FYP. What are these? Obviously, that it depends upon the confinement pressure, and confinement pressure has been dependent on these three: yield stress of the transverse steel, the volumetric ratio of the transverse steel, and confinement effectiveness factor. Now, this actually speaking tends to give you a feeling that the if I use higher strength bar for confinement, I will be better off. Actually not true, because with high yield strength bars, you will tend to reduce the area of steel from the strength point of view, and therefore you will end up having less stiff transverse confinement. And therefore, this model, though this is the most popular model currently being used in most design standard, including the one which has been built into the IRC 112 in its recent amendment, the issue is this model. That is why there are two models. This is the first model. That's why I've marked it in red, meaning use it with care. Don't misinterpret it and stretch it to the wrong direction. This yield strength concept is not a very good effective way to express this. And this volumetric ratio is something that is also not completely correct, in the sense that it says it doesn't matter how you provide the tie, it is just the total volume of ties, horizontal ties to the total volume of concrete. That is all that is important. And finally, there is a confinement effectiveness factor which depends upon, which is been introduced to take care of, if the confinement in one direction is different in its effectiveness from confinement in the other direction, which can happen, let us say, in the case of a rectangular section. So that confinement pressure, you can say you have got the largest confining stress ratio in one direction and the smallest confining ratio in the other direction. Together will give you a curve for effective confining pressure, which will vary from this to this. And if you notice, if the effectiveness of compression becomes zero, this becomes zero, this becomes zero, and you will end up having only this is, which is same as what you end up having as your traditional way, that is an unconfined concrete, is what it will reduce itself to in terms of its simplicity. Now, using this relationship of the effective confinement pressure, then you can determine the variation in this. This is one model which is very commonly used nowadays in determining the effect of confinement. And you will notice that this may be used to some extent in assessment and also in the original design, especially if you are doing seismic design. Okay, the second model, which is little more preferable, but it is not yet the one which you see in Morse code. Morse code, you tend to see the Manders model. In this case, the effective confinement pressure is a combination of two parameters, K1 and FLE. FLE is an equilateral confinement pressure, which in this case is linked to the actual stress in the bar, confining steel. It is not linked to the yield strength of the bar. It is linked to the actual stress in the bar, which is why this Fs is different compared to that. And the fact that the parameter you have, for example, if you take a look at the stiffness of the transverse bar, there are more bars in the if we call this as transverse and this as longitudinal, if we call it, take that, the transverse bars, there are more in area and smaller in length and therefore stiffer in that. So you end up having a higher value of stiffness in that direction. and in the other direction you have only one bar, and therefore, and it's also longer length, so its stiffness is smaller. So you have effective confinement pressure lower in that direction, and therefore you will have a differential increase in the ultimate compressive stress FCP, as well as your uh, strain model that you look for. Now, for long wide column, I want you to think, how will you increase the effectiveness? What kind of detailing will be good for it? That you think about it and come back, assuming that EA by L, which is the stiffness parameter that you talk about, is an important parameter in this direction. The L is very long, A is also small. In this direction, the L is small, A is also very large. So you end up having this kind of a differential. And when you do this, and it is this model is attributed to Razvi and Satyoglu, and you will notice that you have a differential magnitude summation of AS in two perpendicular direction. And remember, this Fs is not the yield stress; it is the stress induced in the steel syrups. So it depends. That means if you want what they call it, a higher stress to be induced in it, then in that case, what you should do is you should go for lower Fy. So it is more effective to stress and area that you want to do. Okay. So if you take a look at this, that you will find that this is the kind of confinement you see. You end up having the flexural stiffness of the bar also becomes important. So flexural stiffness of bar, axial stiffness are quite related in terms of, because it depends upon the section sizes. So you can't have differential understanding of it. So you will notice that due to the flexural stiffness, there is less confinement at this place and more confinement at that. And that is what is reflected in the, and this what tells you that if you want a more uniform confinement, you reduce the spacing of these transverse bars between the ties, distance between them when you do. So if you take a look at this model in its different cross section, so if you take a look at that in a square shape with a tie of this nature, you will end up having, at the places where the ties are effective, will have higher confinement pressure. In between them, there will be lower confinement pressure. And the more number of bars and the more number of ties you have more uniform tie that is taking place. And from the peak to this, the gap is lower, as you can see, compared to the ones with less number of ties. And you have the issue that we have more number of it, so you have a higher confinement in this direction. You have only one bar, so you have lower confinement in pressure in this direction. All this go towards deciding for you what is the permissible compressive stresses in the constitutive relation that you use when you are going to do the confined concrete analysis using this detailing. Now, if you notice, in the first model, in Mander's model, since it's only based on a parameter called the effectiveness and the volumetric ratio, it doesn't distinguish between the confinement pressure in that direction and this direction. But whereas in this model, these two are different. These two are different, and that's one thing that you need to note important in these two. Okay. Now, let's go back and look at the stress strain curves for concretes of 25, 50, 75, and 100. When we provide confinement, what happens to them? So you see, we have a sigma epsilon Cu of 0.0035 for the low strength of M25. And when you do it in confinement, you will notice that this value 0.0035 increases to almost 0.0, almost it increases 3 times. Whereas its effect, as you start increasing the strength, this ratio, the so-called increase in the ductility of concrete per se, it goes on reducing, even with confinement. You can see for this grade, the confinement, the ratio, this has gone down a little bit, but this has gone down a lot from here to here. And for next higher grade. So what does it mean? This is why I would strongly suggest all of you bat for low strength concrete as much as possible. Do not jump into the bandwagon of going for higher and higher strength concrete blindly. you notice what is happening to the internal concrete ductility as the concrete, even in spite of, remember this green graph is with confinement effect, the original curve is unconfined. So you notice that the green, the blue, the orange and the pink are all confined concrete. The impact on the loss of the ultimate strain is tremendous as you increase the grade of concrete. So what does this tell you? That you shall, as far as is possible, not use very high strength concrete. So please do not buy into the fact that high strength concrete are great. Don't buy into that argument at all. Ideally, you should try to restrict your concrete to less than 50 grade. Less than 50. 50 also should be avoided. As you can see from this graph, for the 50, you notice that the so-called ductility has this from 1, it has come to a 0.75 to 0.3. It has become 2.5. From a ratio of 3, the internal ductility is reduced to 2.5, and by the time you come here, it reduces to 2, and here it is marginally more than 1, the ductility in the concrete itself. So therefore, don't ever use concrete of very high strength indiscriminately. Okay, so in the last few classes, I have been trying to, as long as you are designing reinforced concrete structures, you must use the lowest grade of steel possible. Of course, due to the fact that in India they have stopped manufacturing 415 grade steel, you end up having to use 500, but that's still better than going and using McLoy bar 1000 MPa yield strength bars all over the place. Don't do that. And as far as concrete is concerned, what is an ideal range of concrete to use for bridges? After today's class, what is an ideal range? 30 to 50. Okay. Don't get yourself talked into going for higher grade than that, whatever be the reason. Okay. So that is the benefit of confinement. Confining steel improves the ductility in the concrete itself. Now comes the question. As I told you, the peak stress change is very small. The 25 will go to around 32. That's not that much as compared. That's only about 25% or so more. But this is 3 times. This is what is more interesting. As you can notice that epsilon Cu ranges from 2 times the unconfined to the 2 to 3 times it becomes the unconfined one. And this is very small, 20 to 30% only increase in the peak stress. This is where the confinement increasing the strength of concrete is not as interesting as the fact that it increases the ductility of the concrete itself. Okay. So the ductility leads to what? Ductility leads to deformation capacity. All right. Now we come back to the deformation capacity, and I will repeat the old lesson. That fact that deformation is the reality and the stresses are the conjecture. That means we must have an ability to accommodate and higher deformation. There will be certain loading conditions which are more critical. We don't think that the service condition is the most critical, very rarely so. The most critical ones are the extreme events such as earthquake, wind, impact of floating bodies and moving vehicles, or in certain circumstances, blast. So these are all extreme events, and the ability to survive these events depends upon the deformation capacity. And that is where the ductility comes in. And as I mentioned to you, the epsilon U to epsilon Y for steel is in this range, around 300. If you go back and check your the what do you call it, the 14, 15, 16% versus the yield strength of 0.002. That's 0.2%, 0.2 to 15% by 0.2. you will get to 300 as the ductility for steel. And concrete, we're talking about 3, but remember 3 is the maximum. It can be as low as 1.5. But let us say we are reasonable designers. So we are designing for the confined concrete with a ductility of 3 and steel with a ductility of around 300. The combination of these two is what gives us the what we call as the structure ductility. Individual material ductility is fine, but what we require to look at is the structure ductility. So when it comes to structure ductility, if we have to determine the structure ductility being defined as the deflection at the peak divided by the yield line deflection, obviously the structure ductility will be very high when you don't have any P, because of course lateral deformation we talk about, you need to have horizontal forces there, but if the P is 0, you will end up having the highest structural ductility when the P is 0. You will have a H by HP, which is the highest. Now, obviously, that's a theoretical condition. In reality, there will be no bridge pier which will not have superstructure load on it. So once we introduce a superstructure load, then what happens is as you increase the magnitude of P, you will notice that the what do you call it, the peak value at 20% of that itself, you start when you reach the what they call it, the axial compressive stress at 0.2 of Py, the maximum yield strength of this column, you will notice that the ductility which is measured as HB by HB starts dropping. And once the axial load is so high that it reaches the level of 40% of the yield strength of the axial compression of the column, you will notice that the structural ductility drops dramatically. Now, can you tell me why do you think it is happening? And do you think we reach this kind of situation in our design? Or when do we reach this kind of situation in our design? The structure ductility dropping with increasing level of axial compressive stress. Why is it? Why should it happen? So what kind of decisions that we make will lead towards that decrease in the structural ductility being measured as HU by HY? Yes, please. The answer is in the graph itself. Yes. No. Structural ductility is a measure of maximum HU by HY. That keeps reducing as the axial compressive stress goes on increasing. The first case, no axial compressive stress, you keep on applying the HY, HU by HY is the highest at that time. That means you have very high ductility. But the ductility at lower and lower value of HY, the structure tends to undergo failure as you start increasing the axial stress. My question to you was, under what condition will this happen? Under what circumstances will this happen? See, Py is the, when the axial, Py is the yield capacity of the section. So when the applied load P is 0 times Py, you have the highest structure ductility. As you start increasing the axial load Py, once it reaches 40% of your yield strength, the structure ductility drops down dramatically. And why should it happen? And when does it happen? It ties into a few things we discussed a few minutes back. This will happen if you make your pier section size very small. If you make the pier sections very small, then your actual axial load will go much closer to the limiting compressive strength of your column section to the extent of becoming 40%, and therefore you will lose. Therefore, if you go for very small column section, you are affecting your structure ductility, seriously affecting the structure ductility. And another reason why it can happen is you start reducing the section sizes by going for higher and higher grade concrete. Every time you go for higher grade concrete, what is your aim? Your aim is actually to reduce the section size. And once you reduce the section size, your axial load is not going to significantly, superstructure is prefixed, live load is prefixed, your P is fixed. The P as a fraction of P5 will keep on increasing as you reduce the size of the section based on your grade. So therefore, is another lesson for you as to why you should not reduce your section sizes to become too small. We'll come back to this. This also linked to another aspect related to the axial load in the column members, which is buckling. We'll come back to that phenomena a little later. But this is from the ductility point of view. Why does see, ultimately no phenomena is in isolation. So in this sense, for all lateral load caused deflection, the moment you increase the axial load beyond a certain limit in terms of its capacity, you will find that the failure takes place much earlier than it is, and thereby indicating to you that the planned ductility, which is there when you choose your material, when you choose your steel type, you've chosen the structure ductility, but you don't get it because of your design decisions, which link to the size of the section that you adopted. So don't go for too small a size. Don't go for very high grade of concrete. Okay. These are the two things that you should make sure that when you take your design decision, you do not fall into this trap and thereby affect the structure ductility. So you have this ratio of H by HP almost at the level of 3 when you have no load. It's around 2 plus when you have about 20% of the column capacity as your axial load, and it reduces to 1 when the axial load P reaches the level of 40% of your column yield capacity. Okay, so therefore this measure H by HP keeps on dropping, and therefore you will end up having the loss of structure ductility is what due to the presence of axial load in a level when compared to the axial load capacity of the column section itself. So please remember this phenomena very carefully when you're doing out the sizing of it. Okay, now having talked about confined concrete, we achieve the confinement through the provision of reinforcement. And when we have this provision of reinforcement, we automatically create another problem for us, which is linked to the corrosion of this material. This material called steel corrodes. So let us understand a little bit about the corrosion phenomena itself. Now, what happens is it's basically an electrochemical process, and it requires a simultaneous presence of moisture and water. Oh, sorry, moisture and oxygen. Moisture and water are same. Okay. So what happens is, let us say there is a piece of iron and you have a deposition of water in some place and no moisture in some place and no moisture in the other place. Okay, so where there is no moisture, they all become the anode and negatively charged, and in the where there is a water, the electrons are lost into the water, and you end up having the formation of the OH ions there. This establishes a flow path. It establishes a flow path for electrical process to start, and in the process, in this place, in the water, when you also have oxygen available in the form of a dissolved matter, the reaction take place, and the oxygen reacts with water, and it produces the ferric oxide, which is basically the rust. The rust occupies the 6 times the volume of the original steel material, so it causes other effect of this. So the question is, that means what? The process is, the corrosion process is accelerated by presence of moisture, and along with the moisture, the presence of dissolved oxygen. Now, how do you understand? If you can, if you do one thing, do one experiment in your house. When you go back, you have stainless steel spoons or vessels, anything that you have at home, which is in stainless steel. You keep one stainless steel with moisture on it, and one stainless steel which is drier. Keep both of them side by side for a few days and observe what happens. Okay, what did I tell? You keep one piece of stainless steel vessel or an equipment which is having a little bit of moisture on it, and the other one which is completely dry. What do you expect to see after a few days? What do you expect to see? No difference? You might have noticed, those of you who use stainless steel utensils at home, after washing, quite often you wipe it. You wipe it. You can argue, after all, it's stainless steel. Why are you wiping it? One part is, of course, cleanliness. There's another engineering part to that whole process of wiping. So I give you an idea. One stainless steel piece which is kept moist, the other stainless steel which is kept dry. What do you expect to see after a few days? No difference? Yes, please. Anybody? Or you will tell me after you do the experiment. But I can tell you one thing, the one with the moisture, you will find signs of rusting. How will you know it's signs of rusting? You will see the same reddish stain. Please remember that stainless steel also has iron, which when rust produces the rest is dust. The one which is dry will not rust, because the same issue, you need the presence of water to start the initial ionization process, which is what is seen in the, and the dissolved oxygenate, you require it. Obviously, why the dry stainless steel doesn't rust? It is in direct contact with oxygen. So theoretically, oxygen is there, steel is there, oxidation should take place. No, it doesn't take place, because oxidation can take place only with the oxygen dissolved in water, and it's a very small fraction. Unless the second step at the cathode, this reaction, oxygen dissolved in water, doesn't take place, producing this 4 electrons with iron, it will, the oxidation process will not get initiated. So that is why it is important to have both moisture and oxygen for the reaction to take place. And wherever this moisture and oxygen keep getting replenished again and again, the corrosion is the fastest. That is why you might have noticed, if you have followed your IRC 112 from durability point of view, your alternate wetting and dry is the worst. Next worst is permanently in water, and the one which is least affected is totally dry and very little humidity. When you have, that's the one which is the least risky from the point of view of corrosion. Now, in the process of corrosion, there are three parameters that are taking place. One is the mechanical aspect, one is the material aspect, and one is the environmental aspect. In the mechanical aspect, you need to look at stresses, both service stage stresses, residual stresses, fabrication stresses, lack of fit stresses, and the rate of change of strain. This will essentially means, especially for loads which are varying with time, you have the strain changing, and this aspect, the rate at which the strain is changing, is also an important aspect which affects the corrosion in steel. These are all the mechanical aspects which contribute to the corrosion of steel and the rate of corrosion. Then there is a material aspect, which is composition. So certain alloys make it susceptible, certain alloys make it non-susceptible to corrosion. For example, the presence of chromium and nickel in stainless steel makes it corrosion resistant, not corrosion proof, corrosion resistant. Also the microstructure, if it is very fine crystalline structure, it has one behavior. If it's a coarse crystalline structure, it has another behavior. Surface condition, if it's very smooth, it has one condition. If it has roughness, it has another condition. These are all at the material aspects which contribute to corrosion of steel. Okay. And the last one is the environmental, which means oxygen, water coming from the amount of rain, dew, relative humidity, all of them, radiation, precipitation which may contain other ions such as nitrous ion, chloride ion, all because of the presence of other gases in the atmosphere which might come down into the onto the metal due to the rain. And atmosphere which contains sulfur dioxide, nitrous oxide, nitric acid is because of the dissolution of this in the atmospheric moisture, ozone, etc. Acidic particles, all these lead to the what do you call it, a rate of, and where all the three act, that is where your corrosion is maximum. Among all these, mechanical ones are the least influential in terms of the rate of corrosion. The aspect which will be taken care of, mechanical aspects are taken, and the thermodynamic is what is affected by the material, and the chemical kinetics is what is affected by the environmental. Out of these, the most highest contributions are these material and environmental factors, which lead to the maximum of this. Mechanics have got very little, has some effect, but not that much. Most of the corrosion is controlled by environmental and the material aspects of it. And it's an electrochemical process, as we have led to that. And the you have the different type. When you have a significant mechanical and material, you have the fatigue type of corrosion. When you have the mechanical and environment, another type of fatigue type of corrosion. Every time you involve mechanical stress change and the corrosion is induced, you call it as a fatigue type. And then you have a regular corrosion. There is a fatigue induced corrosion and there is a chemical induced corrosion which will happen. And cracking and spalling will lead when all the three of them are active together. That is mechanical, environmental and material aspect. All of them, that's when you see significant cracking and spalling. Okay. Now, the factors that affect the corrosion, there are three. One is the relative size of the anode. Anode, what you saw was the area. As you go back to this stress, anode is the area where you have no water, and cathode where you have the moisture present. Okay, so you have the surface ratio of the water on steel, surface area ratio of the water and steel. That is one important, and it changes with the time of the day. Then you have the next pattern is material, which is the types of metal, carbon steel, stainless steel, etc. And then you have the operating conditions such as temperature, humidity, which is what we call as environment. All these three aspects affect the rate at which the corrosion takes place. It has a significant impact in the sense that, let us say, if you designed a steel section and let us say you had an original beam in which all the various ratios were complying with the codal requirement, and in a corroded beam where you lose about 2 mm of surface, only 2 mm is lost in the corrosion, you will notice that you have the axial area reducing by 17%, you have shear area reducing by 12%, and the moment of inertia dropping by 15%. Now, all this corrosion in this kind of situation has multiple effects. One, obviously, with the reduction in the area at the moment of area itself, you have the total strength reduction. There is no doubt about it. You have also another problem. The stability or the buckling phenomena is introduced because your moment of inertia also has changed significantly. So the stability of the structure strength is also affected. Stability is also affected by the corrosion of a steel section. So it is not something to be ignored or taken lightly. It also has a third in the constitutive relationship. That means equilibrium is affected, strength is affected. The third aspect is stress strain relationship also gets affected. Studies have been done which shows that if your original steel has a pattern of this nature, that means you have this strain hardening and then you have the post strain hardening stress strain curve. As the corrosion rate increases, you will find that you actually are eliminating the whole process of strain hardening and you directly end up having the complete process becomes non-linear. So it affects the constitutive relationship, which is a stress strain curve for steel itself, massive as your corrosion rate increases. Therefore, whenever you're doing the residual life assessment, you have to be very careful in what kind of stress strain curve you're using, depending upon the extent of corrosion that you observe at site. Okay, so what all does corrosion affect? It lowers the ultimate strength. That means this ultimate strength is coming down to here. It reduces the yield strength. So you can see the yield strength also is coming down as the corrosion rate increases. It reduces the lowers the onset of strain hardening. The strain hardening is onset at this strain. So at no corrosion, it is at this strain, and at high corrosion, the strain hardening sets off at earlier. The elongation is also, it reduces, that it comes from this fact that is epsilon Cu, which was here at original at no corrosion, reduces to this level at the 30% corrosion rate. So it affects in all respects, not just a simple loss of area. It also affects at the material level. That's what happens. Okay, so we will stop today's class here. I'll look for any questions from your side that you may have on what you have seen today. Yes, any questions? Yeah, go ahead.
You said that the corrosion reduces both the strength and the ductility of the steel. So is
Yes.
it because of the loss in section, or is it a material property change?
It is combined effect of all. Basically, for the reduced section, now if you what you're telling is, if I take away the corrosion part and I derive these curves as if it is a original section, yes, then for this section, if you calculate, then it will match with that. But for the original section, whatever you assume, it is no more valid. You have to re-establish for your revised section. That is why it is looked at in that fashion. Okay. Yes. All right, if you have nothing further, we'll call it a day today, and I'll see you again next Friday. Okay? Right.